In late summer 1944, a North American P-51B Mustang of the U.S. 354th Fighter Group was forced down near Münster after engine damage from flak. The pilot survived and was captured, but his aircraft, mostly intact, fell into German hands. For the Luftwaffe's testing command at Rechlin, the Mustang represented a rare opportunity. Allied aircraft had been recovered before, but few in such repairable condition. Engineers quickly transferred it to the Erprobungsstelle, the central testing base where captured Spitfires and B-17s had already been examined. The Mustang's arrival came at a critical moment. The Luftwaffe was in defensive collapse, its airfields bombed daily, and its fuel supplies nearly exhausted. Yet technical intelligence still functioned. Analysts wanted to understand why this new American fighter could escort bombers from England to Berlin and still outfight German interceptors. Initial inspection revealed remarkable engineering consistency. The laminar flow wing, an innovation previously underestimated by German designers, produced minimal drag at high speed. The Rolls-Royce-derived Merlin engine, built under license by Packard, delivered steady performance even above 25,000 feet. Most striking was the quality of manufacturing. Rivet alignment, surface finish, and internal sealing exceeded that of contemporary German fighters built under wartime conditions. When Luftwaffe mechanics ran the engine on the ground, they noted the quiet precision of its supercharger, its smooth throttle response, and its reliability at prolonged boost. Test pilots lined up to fly it, including veterans from the FW-190 and BF-109 programs. They wanted to know if the Mustang's reputation for balance and endurance was propaganda or a measurable advantage. Preparations began in early September. Ammunition was removed, instrumentation recalibrated, and oxygen systems modified for German fittings. The Mustang would fly again, this time in German markings over a collapsing Reich, to reveal why its perfection had become a strategic problem. The first evaluation flight took place at Rechlin on September 12, 1944, under tight secrecy. The P-51B, now bearing hastily painted black crosses and a temporary tactical code T9+CK, took off alongside a BF-109G for comparison. German pilots were accustomed to temperamental aircraft, machines that demanded constant correction, torque management, and delicate handling at the edge of stall. The Mustang behaved differently from the first second of rotation. Test logs describe its takeoff as effortless, the torque minimal, its rudder response immediate. The pilot, Hauptmann Hans-Werner Lerche, recorded that the aircraft feels light yet stable, as if it anticipates correction before it is made. At cruising altitude, the impression deepened. Trim stability remained constant through speed changes that would have required continuous input in the Messerschmitt or Focke-Wulf. The cockpit, though cramped by German standards, offered superb visibility, particularly to the rear, thanks to the teardrop canopy later standardized on the P-51D. When engine tests began, data shocked engineers. The Packard Merlin maintained consistent manifold pressure across the altitude range without the irregular surges common to German superchargers. Even at 7,000 meters, the engine provided uniform thrust, something the DB605 could not replicate without risk of detonation. Fuel consumption curves revealed efficiency roughly 15 to 20% better than German fighters at comparable speeds. During high-speed runs, the Mustang reached over 710 km per hour in level flight, just below the FW-190D's best figures, but with far longer endurance. At 500 km per hour, the controls remained precise, with almost no compressibility buffeting. German testers noted that the aircraft forgives error, an unusual statement in reports normally filled with technical reserve. When the aircraft landed after 90 minutes, technicians surrounded it in silence. The data confirmed what combat reports had long suggested. The Allies had achieved a synthesis, range, stability, and reliability unmatched in any Luftwaffe fighter. For the first time, German evaluators used a term rarely applied to machinery, vollkommen, too perfect. Following the initial flight, the P-51B underwent full mechanical disassembly. Every surface, bearing, and valve was measured against German production tolerances. The analysis exposed the gap between two industrial systems, one deteriorating under bombing and material shortages, the other operating at a scale of precision that Germany could no longer match. Engineers began with the Packard-built Merlin Vive 1650-3. Its casting and machining tolerances were uniform to within fractions of a millimeter, each cylinder head identical in weight and balance. The supercharger gears showed no asymmetry or surface scoring even after hundreds of operational hours. German evaluators, used to the coarse finishing of late-war Daimler-Benz components, noted that mass production does not reduce accuracy. In their reports, this single sentence carried strategic meaning. Allied industry had achieved consistency that Germany's artisanal engineering could not reproduce under strain. Fuel system inspection revealed the second secret: high-grade filtration and seamless fuel line integration. The American use of flexible rubberized connectors, rather than brittle metal tubing, allowed quick replacement in the field. It reduced vibration failure by more than half, something Luftwaffe mechanics constantly fought in the Bf-109G series. Attention then shifted to the airframe. The laminar flow wing was measured for contour irregularity. Using a tactile gauge, engineers found deviations so minor they were nearly unrecordable. Wartime German aluminum sheet production could not produce panels of such even thickness. This was not only design genius but industrial mastery. The Mustang's aerodynamic advantage existed because the United States could build uniform surfaces at scale. The final report emphasized an uncomfortable conclusion. The P-51's superiority did not rest solely on innovation, but on reproducibility. Every part fit every airframe, a principle alien to a Luftwaffe dependent on skilled labor and manual adjustment. It was not a pilot's plane alone, it was a systems victory. The second series of flights focused on the P-51's handling through its full performance range. Between September 14th and 20th, test pilots conducted climb, dive, and endurance profiles. Each sortie reinforced a consistent theme. The aircraft was not only fast, it was predictably fast. The Luftwaffe's most experienced flyers were unaccustomed to such uniform behavior. German fighters excelled at burst performance and aggressive maneuvering, but punished small errors. The Mustang instead offered precision without punishment. At climb tests, the Packard Merlin maintained steady output up to 8,000 meters. The rate of climb, measured at 17 meters per second, fell short of the Bf-109G's initial ascent, but surpassed it above 6,000 meters, where the German supercharger lost efficiency. Engine temperature remained stable even after repeated boost cycles, a result of the radiator's Meredith effect duct, which partially converted heat into thrust. The system impressed German engineers, who had experimented with similar designs but abandoned them due to manufacturing difficulty. In dives, the laminar wing and counterbalance controls reduced compressibility buffeting that plagued the FW190A beyond 750 km per hour. The Mustang's acceleration in descent was linear, its recovery smooth, its structure free from oscillation. Reports note, "The control harmony is without precedent. No aircraft in German service maintains such proportional stability." During endurance testing, the P-51 cruised for over 4 hours on internal fuel, twice the duration of any Luftwaffe single-engine fighter. Its drop tank configuration allowed round-trip coverage of over 2,000 kilometers, a distance that fundamentally redefined escort tactics. To German strategists, this range explained why American bombers now reached industrial centers unchallenged. The Mustang's endurance transformed air defense from a tactical contest into a logistical impossibility. Pilots emerging from the cockpit used the same phrase independently. "It has no weak point." For an air force built on exploiting enemy flaws, this was the most devastating discovery of all. The Rechlin evaluators did not test the P-51 in isolation. Parallel flights with a Bf-109G6 and an FW-190A8 were staged to create direct performance graphs. The results exposed a philosophical divide as much as a technical one. German fighters had been engineered for brief, decisive engagements near their bases. The Mustang was built for sustained operations across entire theaters. Every component reflected that difference in purpose. Acceleration trials revealed the contrast immediately. The Bf-109 climbed faster in the first 1,000 meters, but its narrow track gear and torque demanded vigilance. The Mustang, heavier and smoother, could be flown with one hand on the throttle for extended climbs without trim changes. In prolonged turns, its laminar wing maintained lift with less drag, allowing wider radius maneuvers at equal altitude loss. The FW-190, though fierce in roll rate, burned fuel at twice the rate and overheated within minutes at combat power. Instrument layout provided another lesson. German cockpits were cramped and idiosyncratic, shaped by incremental upgrades. The P-51's panel was standardized, clean, and illuminated evenly for night or high-altitude use. The seat harness integrated with the structure to reduce pilot fatigue. An advantage invisible on paper but crucial in 6-hour missions. Engineers marked this feature as psychological range, the ability to fight effectively after hours aloft. Fuel analysis offered the strategic revelation. American 100 over 130 octane fuel allowed sustained manifold pressures impossible with German 87 octane stocks. The difference in chemistry, not just design, let the Merlin deliver both power and reliability. No equivalent fuel could be produced in Germany by late 1944. Thus, the Mustang's superiority was a product of resource systems, not just engineering. The comparative flights ended with a short note in the final logbook. The opponent has achieved total synthesis between pilot, engine, and endurance. We achieved brilliance only in fragments. It summarized a truth the Luftwaffe could not reverse. Germany's fragmented excellence could not match the Allies' unified perfection. After performance comparisons, engineers turned their attention to the P-51's internal architecture. The aircraft's simplicity disguised deep sophistication. Each system, from hydraulic lines to electrical routing, reflected deliberate minimalism. Nothing redundant, yet nothing fragile. German evaluators accustomed to over-engineered assemblies, redundant braces, multiple inspection hatches, layered wiring, found the Mustang's economy almost unsettling. It was a machine that relied on design intelligence rather than constant maintenance. The cooling system exemplified this difference. The radiator scoop under the fuselage, initially mocked by German aerodynamicists as drag-inducing, proved an aerodynamic advantage. Measurements confirmed the Meredith effect, produced net thrust at high speed. German prototypes had achieved similar efficiencies in theory, but failed in practice due to sealing defects and pressure instability. The Mustang's duct geometry, perfectly calculated and flawlessly built, converted thermal waste into propulsion, a feat that required both mathematical precision and industrial consistency. The airframe's modularity impressed technicians most. Major assemblies, wings, stabilizer, and tail section could be replaced in hours using standardized mounts. Field repair reports from captured maintenance manuals confirmed that American depots could rebuild a damaged airframe overnight. In contrast, Luftwaffe field workshops needed days to align a replacement wing on a Bf-109, each one slightly different from factory norms. Inspection of the oxygen and heating systems revealed further contrast in operational philosophy. The Mustang was designed for endurance in Arctic altitudes. Its cockpit remained habitable above 8,000 meters without frost buildup. German fighters required electrically heated suits and supplemental oxygen bottles prone to leakage. Pilots flying long-range sorties in the P-51 remained sharper, physically and mentally, simply because they were warm and breathing normally. Recklin's technical summary captured this in one line. The American fighter is not luxurious, it is efficient perfection. Every screw serves range, reliability, or speed. For an Air Force now forced to ration flight hours, such ruthless functionality was beyond imitation. By October 1944, the Recklin engineers presented their consolidated findings to the Luftwaffe's technical command. The report contained no superlatives, only measurements, but its implications were devastating. The P-51B, operating on American logistics, represented not a superior pilot culture but a superior system. The Mustang's endurance, reliability, and altitude efficiency proved that industrial alignment could outweigh tactical innovation. German command had always treated performance as the product of genius. The individual designer, the ace pilot, the exceptional mechanic. The Mustang demonstrated the opposite. Its excellence arose from conformity, from thousands of identical components built to one tolerance across hundreds of factories. Even its famous agility resulted from predictable balance, not artistic design. It was the triumph of process over inspiration. Fuel and production data emphasized that point. Each P-51 consumed aviation gasoline refined from American crude with precise octane control. Its Packard Merlin required this consistency. Without it, supercharger synchronization would fail. Germany, lacking steady access to high-quality petroleum, relied increasingly on synthetic fuel, whose unstable composition eroded reliability. Thus, even if Germany had copied the Mustang outright, its performance could never have been reproduced with available materials. The test pilots, though impressed, recognized the strategic verdict. The P-51 was the physical proof of a logistical empire. It symbolized a kind of warfare Germany could not fight, one that depended on integration rather than improvisation. The Luftwaffe, brilliant but fragmented, was meeting an opponent that had converted precision into policy. In the final pages of the Rechlin report, a short annotation appeared in pencil beside the performance charts. This machine is perfect within its concept, and that is its true danger. It was not admiration. It was a technical epitaph for an air force whose creative chaos had finally met disciplined perfection. After the final flight evaluations, engineers at Rechlin considered whether aspects of the Mustang could be replicated or adapted to German aircraft. The answer, even in internal memos, was pessimistic. Every major advantage of the P-51 was inseparable from the industrial context that produced it. Germany could understand it, but not reproduce it. The laminar flow wing, for example, required extremely smooth skin and tight manufacturing tolerances. Wartime aluminum production in Germany had degraded by 1944 due to alloy shortages and rushed output. Rivet alignment tolerances that the Americans held within tenths of a millimeter were impossible under air raid conditions. Attempts to refine panel finish on a test FW190D proved futile. Vibration during flight immediately cancelled the benefit. The technology worked only when executed with near-perfect precision. Engineers also studied the radiator's Meredith effect duct to adapt it for the TA-152 high-altitude fighter. Calculations showed potential performance gains, but the complex contour shaping required dies and machining capacities that no longer existed. Rechlin's chief designer summarized it bluntly. The system can be drawn, but not built. Even the cockpit ergonomics, admired for their clarity, reflected a standardized production culture foreign to German industry. The Americans produced thousands of identical panels. German aircraft still relied on supplier variations, handwritten annotations, and field modifications. The P-51 simplicity required a bureaucracy that treated design uniformity as strategy. A few features were incorporated experimentally: smoother control linkages, longer-range fuel tanks, and improved canopy visibility. Yet all were stopgaps. Nothing could match the combination of power plant reliability, aerodynamic efficiency, and strategic logistics that made the Mustang unique. By winter 1944, Rechlin's captured P-51 had been flown nearly 40 times. It remained intact, meticulously logged and increasingly symbolic. A silent demonstration that the war was no longer a contest of design brilliance, but of endurance, organization, and scale. The technical revelations from Rechlin filtered through the Luftwaffe's hierarchy during the last months of 1944. Fighter leaders and design bureaus drew different conclusions, each reflecting the desperation of their situation. Operational commanders saw the Mustang as an unavoidable symbol of Allied dominance. Designers viewed it as a benchmark they could not match but might learn from. At Jagdgeschwader headquarters, pilots who had faced Mustangs firsthand were unsurprised by the test data. They already knew its endurance meant that no German airfield was safe. What shocked them was the absence of mechanical weaknesses to exploit. Traditional Luftwaffe tactics, vertical dives to exploit climb advantage, rolling scissors to lure opponents into stalls, were nearly useless. The P-51 could dive with the FW-190, climb nearly as well as the Bf-109, and outlast both. Its operational ceiling and range erased geography itself as a defensive factor. At Messerschmitt and Focke-Wulf design offices, the reaction was analytical rather than emotional. Engineers confirmed that the Mustang's perfection was systemic: aerodynamic efficiency married to industrial uniformity and sustained fuel quality. Kurt Tank's team, while finalizing the TA-152, admitted privately that even their masterpiece would be produced in dozens, not thousands, and each with different quirks. German aircraft design remained dependent on individual craftsmanship. The Mustang embodied reproducible exactness. Luftwaffe staff officers debated the report's closing recommendation: avoid duels with P-51s and focus on bomber interception. It was a reluctant admission that the enemy fighter was untouchable under equal conditions. Strategic memos began referring to Allied air superiority not as a phase but as a permanent environment. In the mess halls and hangars of the collapsing airfields, pilots began using a bitter phrase, "zu gut, zu kämpfen," too good to fight. It captured the mood perfectly. The Mustang's flawlessness was not just an engineering feat, it was the mirror reflecting Germany's irreversible decline in the air. By early 1945, the captured Mustang at Rechlin had become both a prize artifact and a quiet condemnation. Test flights ceased as fuel and pilots grew scarce, but the accumulated data circulated among remaining technical staffs. The summary was unmistakable. The P-51 represented not a single breakthrough, but the maturity of an industrial civilization capable of turning design, metallurgy, and logistics into one continuous system. The Luftwaffe could measure it, but not match it. When the last analysis was filed in February, engineers wrote their conclusion in plain, restrained language: performance is optimal, deficiencies, none of consequence. That phrase, keine wesentlichen Mängel, had never before appeared in a German evaluation of an enemy aircraft. For men trained to find fault, this admission was both respect and defeat. The Mustang's perfection carried strategic weight beyond engineering. Its presence allowed the Allies to maintain constant bomber escort deep into the Reich, dismantling industry without reprieve. German jets like the Me-262 appeared too late and in too few numbers to reverse the outcome. What had begun as a captured curiosity had ended as proof that the balance of war had shifted irreversibly toward industrial precision and systemic reliability. After Germany's surrender, Allied intelligence recovered the Rechlin test files intact. American analysts reading them in 1946 found a phrase scrawled in the margin of one pilot's logbook: "Zu vollkommen, der Mensch ist das schwächste Teil." Too perfect, the human is the weakest part. It summarized both admiration and inevitability. In retrospect, the Luftwaffe's verdict was prophetic. The Mustang had shown that technology, when aligned with supply, discipline, and scale, could become self-sustaining. A machine not just built for war, but for endurance. Its perfection was terrifying, not because it was flawless, but because it proved that perfection itself had become a weapon. If you enjoyed this video, don't forget to like, comment, and subscribe for more World War II stories.